is reacted at high temperatures with nitrogen to produce 0.378 grams of a solid Mg, X, and Y. So you don't know the X and Y, that's what you're trying to find. First, you convert the grams to moles of each element. So write as much of the reaction equation as possible. So you've got magnesium and nitrogen making magnesium nitride of some sort, MgXY, MgX and Y. Then you want to use the clues to determine the grams of each element. So in this case, we got 0.273 grams of Mg and 0.378 grams of the product. So how do we determine how much of this we have? Okay, subtract, very good. This plus this has to equal this due to the law of conservation of mass. So 0.273, that's our grams of magnesium. Subtract that from the magnesium with the nitrogen and you get 0.105 grams of the nitrogen. That's what is due to form in this reaction. So now you have the masses. So once you have the masses from the reaction information, convert the grams to moles. So same thing here, grams to moles. Which one is smaller? Looks like the bottom one. So Mg over N, top divided by bottom equals 1.498. Now is that a whole number? Now what do we have to multiply the whole thing by then? Multiply the whole thing by 2. So if you change this to subscripts, okay, 1.498 is not equal to 2. It's not equal to 1 either. So 1G, 1.498N, that would be a good formula, but it's not good enough. We multiply the whole thing by 2. Mg 1.498N2 is Mg3N2. And this here would be our formula for this particular compound known as magnesium nitride. Any questions, clarifications on this? Yes?
Can you go to the previous slide, please?
Previous slide, yep. So, there we go. So this is how we get the ratio of magnesium to nitrogen. Back there. Questions, clarifications on this? Yes, sir.
At the bottom, the 0.0113 grams or moles.
This is in moles. Both of these are in moles. They should say mole ratio.
And then on the next slide, convert to grams.
Correct. This is moles. Well, no, I'm sorry. Once you have moles here, on the next slide, you use the moles to get the formula. So you do not convert it back to grams. So the 1.498 is how magnesium, there's 1.498 magnesiums for every 1 nitrogen. And then if you multiply the whole thing by 2, you get about 3 magnesiums to 2 nitrogen. So some people like to do it here. They go 1.498 over 1, and then multiply the whole thing by 2, and you get the right ratio. Some people like to put it in the equation, and then you get to multiply it out at that. I mean, not the equation, pardon me, the formula. You get that. So this is still in moles, because moles gives us the amount that we're counting. Grams only allows us to convert to moles. And once we have moles, then we can get our formulas. Now, if you have the empirical formula, the next step is to determine the molecular formula. What formula could this be if you have a particular example where the empirical and molecular do not match? So, the first step is to determine the empirical formula. God bless you, just like we did. The next step is to calculate the empirical mass, so molar mass of the empirical formula. Then you want to determine the molecular mass, or the mass of the molecule that you're working with. This is usually given, or you would calculate from other clues. So I'll give you the molar mass, or you'll have to calculate it yourself from other information. Then you calculate your N, which is molecular formula mass over empirical formula mass. And then multiply it out, apply it to all subscripts in the empirical formula, and that gives us our molecular formula. So those are the 5 steps for determining a molecular formula. So, steps in determining molecular formula, how would we go about doing this? What would this look like? So, this here would be a substance. Adipic acid contains 49.32% carbon, 43.84 oxygen, and 6.85% hydrogen by mass. The molecular mass of the acid is 146 grams per mole. The first thing we would have to do before we did any molecular formula is the empirical formula. So the first thing we do, empirical formula. For this, determine its empirical formula, we would have to use the 49.32, 43.84, and the 6.85%. Okay? We convert those into grams by assuming what? 100 grams. So what I'd like you to do right now is determine the empirical formula of adipic acid, and then we'll go through the molecular formula together. All right, step by step. If you've got this, I will ask that you are quiet while we go through it quickly. If you don't have this, then you can obviously check your work and see where you could have improved. So, the first thing is 49.32%. You've got carbon, you've got oxygen, you've got hydrogen. The carbon, you assume 100 grams, 49.32 grams. Okay, then we take our molar mass of carbon. For carbon is 12.01. For oxygen, we do the same setup, but we're converting 43.84 grams. Oxygen's molar mass, 16.00 grams in 1 mole. And for hydrogen, it's 6.85 grams times 1.008 grams in 1 mole. So we take our 49.32 divided by 12.01. This gives us, is that right? Yeah. 4.10657. And then our 43.84 divided by our 16. And this gives us our 2.74 moles. Again, this is moles of carbon, moles of oxygen, and then our 6.85 divided by 1.008 equals our 6.7956 moles of the hydrogen. Okay, the next step is to find out which one is the smallest. It looks like the oxygen is here. So oxygen to oxygen is a 1-to-1 ratio. Then we do the carbon to oxygen. 4.10657 divided by 2.74, and this equals approximately 1.49875 carbons to 1 oxygen. And then our 6.7956 divided by 2.74, and this gives us that 6.7956 divided by 2.74, and this gives us 2.48 moles of hydrogen to oxygen. Yeah.
How much specificity do you want? I mean, there's like for here, like 1.498 divided by 1.5.
Yeah, so keep it the way it is until you find out how close it is to the ratio. You don't want to round too early. We could round it to 1.5 now. You want to keep as many digits as you can here, usually at least 4 digits. Once you divide. So once you divide here, now you've got your ratio. Yeah. If it's 1.75, keep it as 1.75, because then you'll have to figure out what its ratio is, and that could change the fraction. Yeah, it's a hard problem to do, but then you would keep it as it is until you get the actual decimal. The actual whole number ratio. Yeah. So whenever you're in doubt, keep it. So here we've got our C, our O, and our H, which is 2.5. So now you can see this is our empirical formula, but it is not, again, whole number ratios. So if we multiply the whole thing by 2, that gives us carbon, 3 carbons, 2 oxygens, and our 5 hydrogens. And this is commonly written with carbon first, hydrogen second, and oxygen third. But either of those would be acceptable answers for the empirical formula. Yes?
How do you determine which element goes where?
Usually the one to the left of the periodic table goes first. Hydrogen is a unique one because it's usually just written to the right of carbon, so it doesn't usually affect it. Although, when it's written first, it says it's an acid, but it's usually written after the carbon itself. And that has to do with its molecular bonding. So you wouldn't know that from the problem. Yep.
So is there a certain way you put the letters? Does it matter?
For these compounds that have carbon, hydrogen, and oxygen, carbon, then hydrogen, then oxygen is the common convention. But it would not matter if you were looking for an answer here. It would still be okay. Yeah.
Since you said for acid, hydrogen comes first, does that mean in the molecular formula, or like even in the empirical formula, you should write it as like H first and then C and then O?
Yeah, so this here is an example of an acid. This here is an acceptable answer here with the C, H, and O. Again, if you knew it was an acid, you could have, again, the H, C3H4O2. However, there would be some things you would have to know about this and this here and know what ion it was. So it would be a little harder to write. This here is usually the most common answer written initially, and then as you get more information, you would have to know the charge on this ion here, the C3H4O2, or the thing that gets tricky is sometimes these acids here, well, sometimes the nomenclature on the acids can change what the formula is given. So technically speaking, yes, all 3 of these would be correct. The most likely answer that you would see on the answer key would be this. Yeah, but they're all correct, it's the same ratio. But all of these are empirical formulas. None of these are actually the acid itself. So because these are empirical formulas, C3H5O2 is what we have as the empirical formula. Sorry, I was getting ahead of myself. The empirical formula, so that means it is a multiple of this to some power, and we want to find out what n is. So for this, we need the molecular mass over the empirical mass, or molecular weight over empirical weight. So for the empirical here, we would have 3 carbons plus 5 hydrogens. Oh, extra O there we go. Plus our 2 oxygens. So 3 times 1. So So that is 73.07 as the empirical. And then the molecular weight, that is either given to the problem or we have to calculate that, which is 146. So as you can see, 146 divided by 73.07 should give us a good whole number ratio. This happens to be 2/1, or n equals 2. So n equals 2, that means you got C6H10O4, that's a 10 there. That is its molecular formula. So that's how to determine the molecular formula.